How to build and use symbolic logic truth tables. Hi, I'm Pete Facione, co-author with Carol Gittins of the book Think Critically. This presentation describes how you can construct and apply truth tables. This method works with our book and with any other textbook on the topic of truth tables. A truth table is simply a tool for representing or displaying all the values, true or false, of a complex symbolic logic formula. Before building truth tables for more complex formulas, we'll first review the powers of the different logic functions. We'll begin with negation and then move on to conjunction and disjunction and the conditional in future slides. The statement that we're seeking to evaluate, which is on the right-hand side of the table, may use the same statement letters more than one time. Nevertheless, we list each statement letter in that formula only once in the left-hand side when we present them in alphabetical order. No matter what order they appear in the formula we're seeking to evaluate, on the left-hand side, each statement letter listed only once appears alphabetically. In this example, P, then Q, then R. If we've generated the correct number of rows given the number of statement letters we're dealing with, and if we've correctly distributed T's and F's on each of those rows to each of those letters, then four things will be true. First, the top row will be all T's. The bottom row will be all F's. Each of the rows will be different than any of the other rows, and every possible combination of distributions of T's and F's to those statement letters will be represented on one row or another of the table. To determine the value of a more complex statement, in this case our target disjunction, we must first find out the values of its component statements. To do this, we will let each of the component statements be the head of a given column. On this example, the disjunction, which is itself rather complex, becomes the head of a column just to the left of the target statement. We don't need to create another column for the other disjunct in this target because Q, on the far right of our target statement, already is the head of a column back on the left where we have the statement letters. Whenever we want to know the value of a complex formula in a truth table, we know that we must find the values of its component parts. In this example, we take the disjunction, which is itself composed of two formulas, and break out those two formulas so that each becomes the head of its own column. One, as it turns out, is the negation of a conditional, and the other is a conditional statement that has the negation of P as its antecedent. We fill in the values under the various component statements by reference to the powers of the logical functions which create those internal component statements. For example, not P will be true whenever P is false, and not P will be false whenever P is true. So we look at the column that is under the letter P and then apply the negation to the value of P on each row of that column. Similarly, for the formula if R then P, we know that the conditional will be false whenever the antecedent R is true, and the consequence, in this case P, is false. And that does happen on certain rows of this particular truth table. The truth table now displays the value of our original target formula, as complex as it was, under every possible combination of the assignment of the values of true and false to each of its three component statement letters. Our strategy in building this truth table was to work our way up from the simplest internal component statements until we have finally arrived at a value for the entire larger, more complex target statement. We'll use this same strategy in all truth tables. To test whether one formula A implies another formula B, we form the conditional of those two formulas. If A, then B. We then build a truth table for that conditional. If it turns out to be a tautology, which is true on every row of its table, then yes, at this level of logic, A implies B. Let's now put together what we've learned about truth tables and about implication to form a test for the validity of arguments at this level of logic. In our little example, we have two premises and a simple conclusion, the letter Q. If the argument from these two premises to Q is valid, then we could say that the conjunction of the premises implies the conclusion at this level of logic. And we can use a truth table to test whether or not this implication holds. test an argument that is in English or in any other natural language for validity at this level of logic, first translate that argument into symbolic notation. In our book, Think Critically, Dr. Gittins and I explain the process of translation in some detail. We hope you've enjoyed this presentation on truth tables and you found it useful. Thank you very much, and we'd welcome your comments and suggestions. My email appears on this slide.